So like we saw in the last video, current electricity is one of the three types of electricities, and it's the continuous flow of electrons measured in amps. So again, in this diagram, the electricity is flowing. This is the current flowing through this circuit. We've used that word circuit a few times. Now this is the actual definition. So a circuit is just the path that current flows through, electrical current. So in this diagram, the battery is the source of power, which we'll talk about in a minute, and all the red arrows are showing the path the electrons are flowing through. So this is a picture of a circuit. All circuits have three parts, which we'll talk about in a second. But the essential part of this is that the circuit must be closed to allow the flow of electricity. So you'll notice whenever this switch opens, it shuts the circuit off. So electrons need a nice clear path to be able to flow through. When that path is broken, they can't flow anymore. So as long as the path is closed, the circuit is complete. It works. When it opens, then the circuit gets messed up because the electrons can't flow through anymore. And it makes sense. Think of driving your car down the road. It needs a road to be able to drive. If all of a sudden there was no road, you couldn't drive anymore. Electrons are kind of the same. They need a clear path to be able to move. The path that they take is called a circuit. So like I mentioned earlier, we need a power source to make a circuit actually work. In the lab, you used the batteries to be able to light the Christmas light. So voltage is just the power. In the cases that we'll be using in labs, most of the time it will be a battery. So the voltage is the amount of current that could potentially flow through something. It's measured in volts. So in this circuit, you have a battery, which is lighting up the light bulb, very similar to what you guys did. Something that I hope you noticed is in order to light, for example, more of the Christmas lights, you needed more batteries because you needed more power. More lights were taking up more current, so you needed more power, voltage, to be able to light the extra lights. So to be able to do more electricity, you need more voltage. So for example, if I wanted to start my car, I couldn't just use a little AAA battery. I would need more voltage. I would need a bigger voltage source. I would need something like a car battery, which this is a picture of. You needed just a small, like a AA battery to light a Christmas light. If I needed to light 8 Christmas lights, I probably would need about 4 AA batteries. So as the electricity need increases, your need for voltage increases. So the bigger the voltage source, the more current can flow. If it's a small voltage source, you can't get as much current from it. So again, another example, when you were using the snap circuits, if you wanted to light up more lights, you would probably have to add more batteries to the pack. If you wanted to light up more of the Christmas lights, you would probably have to add more batteries. You would need more voltage because you were creating more current.
To make a circuit, you need 3 parts: a voltage source, which is usually a battery, a conductor, which is usually a wire, and something to use the electrical energy, for example, a light bulb. So in these labs, all we've used for voltage sources has been the batteries. But there are other sources potentially, such as like a power plant, an electrical grid, electrical box. Those are all potential voltage sources, but they're a lot more powerful, which is why we use the batteries, because they're a lot more safe. Conductors, again, usually wires, and something that uses the electrical energy that you're making. So it could be a light bulb, it could be a doorbell, it could be an alarm, it could be really anything that uses electricity. So down below are 2 diagrams. The one on the left is sort of a fancy picture. The one on the right is the actual diagrams that I want you guys to know how to draw. So if you're an electrical engineer, if you're an architect, you will know exactly what this means. So these are universal symbols throughout the world. If I went to Sweden and I needed to build an electrical circuit for some reason, it would still be the same exact symbols. So this series of lines represents a battery in an electrical circuit diagram. A switch is a line segment represented here, and a light is basically just a circle like we did with the snap circuit labs. And again, just to quickly revisit this part, because it's very important. In order for a circuit to work, it has to be closed. So a closed circuit means that the electrical current path is not broken. So the switch is what's responsible for opening and closing a circuit. So if the switch is open, the circuit is off because it's been broken. If a switch is closed, the circuit is on because now the electricity has a nice clear path to flow through. And there are two types of circuits. There are series circuits and there are parallel circuits. You built both of these types in the Snap Circuit lab. First one we'll talk about is the series circuit. In a series circuit, the components are lined up along one path. If the circuit is broken, all the components turn off. So this picture below we've seen it many times, but this is actually a series circuit in action. So when the switch opens, the entire series shuts off. The entire circuit stops working. Just like Project 5, if you removed one piece, both the fan and the light bulb turned off. The opposite of that is the parallel circuit. In a parallel circuit, there are several branching paths to the components. So if the circuit is broken at any one part, only the components on that part are going to turn off. So this was Project 6. You could unplug the light, but the fan would still work. Or you could unplug the fan and the light would still work. And this is the type of circuit that's most common in houses, basically in most electrical items. Because if my light in my kitchen turns off, I don't want every single electrical appliance in my house to then turn off. So luckily, that doesn't happen because all household wiring are in parallel circuits. So if my light bulb in my kitchen goes off, everything else will still work because the kitchen light is on its own branch. It's basically its own circuit. So most household wiring are parallel circuits because, like I said, you don't want to lose everything in your house if just one thing turns off.